Two general rules that we have from chemistry. Rule number one, the shorter the bond length is, in general, then the stronger the bond is. And rule number two, the more covalent or the more polar a covalent bond is, the stronger it is, although that doesn't always pan out because there can be other factors that might decrease the bond strength, as we just saw in video on number 2. But again, the shorter the bond, in general, the stronger the bond. And let's just consider a couple of simple examples to illustrate that. Suppose that we have a single bond between carbon and fluorine. Here, the bond length is about 1.33 angstroms. If it's with chlorine, chlorine is a larger atom now, then it's 1.77 angstroms. And then bromine, that's even larger, that atom, so the bond is larger. And then for iodine, it's larger still, it's 2.13 angstroms. To break this bond takes about 108 kilocalories per mole. So if we had a mole of these type of compounds, we wanted to break that bond, it would take 108 kilocalories. For here, where the bond is longer, it's 81 kilocalories per mole. Here, 66. And here, 51 kilocalories. Again, the longer the bond is, the weaker it is. But again, as you saw in the previous videos, there can be other considerations that might disrupt our convenient pattern. For example, suppose we have 2 chlorine molecules. Here it takes 57 kilocalories per mole. So if we had a mole of chlorine molecules, it would take 57 kilocalories to disrupt all those bonds. If we have bromine, a larger atom, a longer bond length, it only takes 46 kilocalories. And if we have iodine, larger still, it takes only 36 kilocalories to disrupt a mole of iodine molecules. What about fluorine? This would be the shortest bond because fluorine is the smallest atom, but yet here it only takes 37 kilocalories to break apart a mole of fluorine molecules. Why so? Again, remember that for the halogens, if we consider just a simple Lewis dot structure, here we have unshared p electron. There's no hybridization here, as we discussed in the previous video, just simple overlap of the p orbitals. These are the s orbitals here, the 2 s orbitals. But here we have p orbitals, lone electron pairs in p orbitals, here, here, and here. So you have all these lone electron pairs that are brought very close together because of this short bond, because fluorine is a small atom. As a result, we have all these repulsions here that decreases the strength of the bond. So even though fluorine has the shortest bond length, it is also one of the weakest bonds in the halogen series, again because of the effect of the unshared lone pair p electrons. So in chemistry we can have some hard and, or we can have some general rules, no hard and fast rules, because there can always be different factors that are going to disrupt whatever convenient patterns we think we may have established. And again, in the previous video we discussed this with carbon atoms, where here two carbons joined together with a single bond then had 83 kilocalories per mole. If we have the more polarized carbon-oxygen bond, polarized, therefore we expect the bond to be stronger, but it wasn't. This was only around 86 kilocalories. And again, as we saw, it was because of these sp3 unpaired electrons destabilizing our bond. If we have with nitrogen instead of carbon, then it's about 70 kilocalories per mole. So now notice this is significantly less than what it is for the carbon covalent bond. Here what is happening is, again, this is for a single bond, this is sp3 hybridized, so we have, let's just consider a block orbital diagram for nitrogen. Of course, we have the paired two s electrons, and then in the p orbitals a single electron. And again, for a single bond, all of these become sp3 hybridized, so we have 4 equivalent sp3 orbitals. Single electron, single electron, single electron to form 3 bonds, and then the unshared pair of electrons here. Now with oxygen we had 2 lone pair electrons, and here then the resulting bond was not as strong as what we expected, because the oxygen is so electronegative. Here we only have 1 lone pair of electrons to disrupt or to destabilize our bond, but yet this is much weaker. And the reason probably is because nitrogen is less electronegative than oxygen, therefore the sigma bond that is formed is not going to be as strong to begin with, and then it's going to be further disrupted by this lone electron pair. Now, to compare what happened in the previous video, if we have a double bond here, then the nitrogen is now sp2 hybridized. And the resulting bond is 147 kilocalories per mole. Again, more than twice as strong as the single bond, as we saw happening in the previous video when we had a double bond between carbon and oxygen. And again, the reason is now the nitrogen is sp2 hybridized, so we can imagine happening something like this, where here we have this, this, and this, giving us equivalent sp2 orbitals. And then we have a single unhybridized p orbital with its single electron to form the pi bond here. these are now 120 degrees apart. So again, with our lone electron here, these were sp3 hybridized, so we have that tetrahedron, everything is closer together. Here it's 120 degrees apart, they're spread further apart, therefore whatever destabilizing effect the lone electron pair has is relieved here, so we probably have a stronger sigma bond here than what we did here, so that overall, when we form the double bond, now once again we see more than a double of the strength, whereas between when we had it like this for carbon, this was like 147. This was less than twice the strength here, because with the carbon there's no lone electron pairs to destabilize our single sigma bond to begin with. So it's sort of like an artificial strengthening that we're seeing here. With the spreading out here of the electrons, this has a less disruptive effect, a less destabilizing effect on the bond than what it does here. So here we're seeing a relief of that. And if we have a triple bond, now in this case the nitrogen is sp hybridized, so an s orbital and a p orbital give two equivalent sp orbitals, and we have two unhybridized p orbitals, each with a single electron. These, of course, will participate in forming pi bonds with the sp hybridized carbon atom, as we saw in the first video. That's how we get these double bonds here, plus our single sigma bond from overlap with the sp orbitals. But here then, the lone electron pair is 180 degrees away from the rest of the atom. Now here then, the bond is 210 kilocalories per mole, 3 times what it is for just the single bond. But again, when we have these two carbon atoms and we form that double bond, we don't see that extra strength. This was 147 kilocalories. And again, it's not because the pi bond is necessarily weaker between here and here and here. It's just that when we have the nitrogen and the oxygen atoms, the sigma bond, the single sigma bond, is destabilized because of the lone electron pairs. So that as we're forming the double and triple bonds, we're changing the hybridization of the nitrogen. We are then giving relief, the crowding of the lone electron pair that's more spread out. Therefore, there's more relief in the repulsion that it generates, so that these sigma bonds that exist here and here are probably stronger than what you have here, and that's why we're seeing the increase in bond strength, not necessarily because the pi overlap is superior. So again, we just want to give a couple of straightforward examples of how lone electron pairs can destabilize a bond. How much they destabilize depends upon the hybridization of the atom. If it's an sp3 hybridization where things are more crowded together, then it's going to destabilize more than when you have an sp2 or an sp hybridization where things are more spread out, and then our lone electron pair is not so repulsive. Okay, that'll be it for this video. In the next round of videos, then, we're going to concentrate on different types of electron delocalization and the p orbitals. what is known as resonance, an extremely important concept in organic chemistry. We hope we can provide a lot of meaningful examples. And again, the playlist for all the videos is at the website digital-university.org.